So the next case setup is laminar flow over an oscillating cylinder. So these are the parameters. So we will be simulating a transient incompressible laminar flow across an oscillating cylinder. So we will be simulating for Reynolds number of 200, which is the laminar regime, and the diameter of the cylinder is 1 meters, and we have velocity of 2 meter per second. The oscillating amplitude is 0.5 meters, so the amplitude of oscillation, and the frequency is 0.5 hertz. We can also represent this amplitude and frequency in terms of non-dimensional values like the reduced frequency and the non-dimensional amplitude as well. So in papers, in literatures, we will find mostly the reduced frequency and non-dimensional amplitude H. So, but for our simplicity, I have used these dimensional parameters in these slides and in the cases also. So you can see the boundaries in our. We can see the boundaries. So we have the inlet, we have the outlet, top and bottom, and front and back is still empty because we are doing a 2D simulation, and the velocity at the inlet is 2 meter per second. Okay, so this is our case structure. So now the case structure is different, slightly different than the previous case structures. So I have highlighted here. We have additional files in our folders, like in the boundary condition folders. We will have a separate file for the point displacement where we will assign the dynamic parameters, and we also will have a file called the dynamic mesh dict in our constant folder. So in this dynamic mesh dict, we will assign which solvers do we use for dynamic meshing, and so yeah, the solvers that we will be using for dynamic meshing should be assigned in the dynamic mesh dict, and the parameters of our motion of our movement will be assigned in the point displacement file. So we will be choosing turbulent model as laminar, and we'll be using a morphing mesh dynamic meshing strategy. So there are different dynamic meshing strategies available in OpenFOAM, like the morphing mesh, adaptive mesh interface, adaptive mesh refinement, overset mesh. So these are the various dynamic meshing strategies. But now in our case, we'll be using morphing mesh. So morphing mesh means there is a physical distortion or the physical deformation of the mesh. So we can see that our mesh is moving, uh, like the AMR case where the mesh is split into many more meshes, that it gets refined into smaller cells, smaller meshes. But in the morphing mesh, the the mesh will deform and distort as the boundary moves. So this is advantages for like the large deformation or the large displacement boundaries. So if the displacement of the boundary, that the oscillation or the plunging or the pitching is more, then this might lead to divergence problems, and we need to monitor the current number and time step very carefully for these cases, for the cases of morphing mesh. Okay, so now let's look in our case structure. Okay, now I'll show you first how to download, where did I download this case from. So if you go to our FOSSEE case study repository, and you can see the case study project. So under completed case studies, so if you go to number 44 case study, in the 44th case study, you see that there is a case study for laminar flow across an oscillating cylinder. So you can download this case study first. So I have already downloaded in my system. So let me show you that there are some changes that needs to be made, because these case studies have been run in the very older versions, and in the newer versions there might be some keyword errors, like it asks for new keywords and new syntax. So you need to look at those errors and debug it on your own. So let me show one such case. Like somebody had also asked, like, if I have installed OpenFOAM 13, then if does it run in OpenFOAM 9? So that might not run because and throw some errors, because uh, this there because in the newer version that there might be changes in the syntax and keywords. Okay, and while we while we keep our rename when we rename our file, we should not keep any spaces in between our files, in between our words. So if you keep spaces, then that will give throw errors. Okay, so after you download this and after you extract this, you can get the you can go inside of it. So you can see that there is a folder called case files, and we can observe that in the case files there is a space between the case and the files word. So this will also create the error. So you need to first remove this space. Now and this in inside it there is no any all run file because these are the previous older cases. So I think the all run files are missing. But in the newest newer case studies, we can all find the all run all clean files and readme files. So you can see that it says the cannot find file system block mistake. So in the previous structure, you can see that uh, the blockmesh dict is inside the constant folder inside polymesh. But in the newer in the version higher versions, we need this blockmesh dict in the system folders. So we need to copy it back into the system folders. So now let's learn black blockmesh. So now you can see that the mesh is generated. Now there is an important command in the for the dynamic mesh, so that is which is move mesh. So if you type move mesh, then this will move the mesh. That only it will not solve for the flow parameters, but it will just move the mesh. So you can also show that you can also see that there is an error thrown here. So it said that keyword motion solver is undefined in dictionary this the laminar horizontal and in this file. So in dynamic mesh dict, it says that the keyword motion solver is undefined. So in the newer versions, what it is required is in the older versions, just the solver keyword was used. Now in the higher versions, so it requires keyword called. So you can see that keyword motion solver. So just you need to replace that with motion solver, motion solver, and okay, I think there was an error. Motion solver. Now let's run move mesh. So move mesh, it won't solve for the flow parameters like pressure, velocity. It will just uh, solve for the deformation of the mesh. That is the mesh deformation. It will solve and so. So now you can see that our cases is now the case is running. So I was just trying to show that how in different versions the keyword errors can be present, and then the case then the case folder structure might be different. So you need to look at the errors in the terminal and then debug them accordingly. So I have already run this case, so I won't run this. I won't run it now again. So let me see. So this is the case that I have already run. So let me explain basically on the two important files, that is the dynamic mesh dict file and the point displacement file. So you can see that I have chosen the plunging amplitude as 0.5 meters and the frequency at 0.5 hertz, which means that my time period is 2 seconds. So for to keep that, according to this input parameters, so I have to make changes in the point displacement file. So before point displacement file, let me also explain the dynamic mesh dict file. Okay, though it's in a constant, then we missed it. So you can see that the motion solver that we have used is displacement Laplacian. So there are various solvers in OpenFOAM that will accommodate the dynamic meshing strategies. So the one motion solver that we have used is that this is displacement Laplacian. There are other motion solvers like the velocity Laplacian, SBR stress rotational. So there are many other types of motion solvers that we can use. So you can also look at the SRC folders and see the available motion solvers or the solvers libraries that are present in the open form to for dynamic meshing. So after we also choose the diffusivity value. So the diffusivity value chosen is the inverse distance. So the inverse distance means that the deformation will decrease as the distance from the moving body will increase. So as the cells from the moving boundary is will be far, the farther cells from the moving boundary will be less affected by the displacement of that boundary. So this means the inverse distance means that. So after we assign the solver, then we need to assign the dynamic parameters like the amplitude and the frequency. So we can see that the Australian displacement is used as the motion function, and we have used the omega as 3.14. If you calculate based on this parameter, so you will get these values. So if you get based on 0.5 Hz, and then we have used amplitude in the y direction at 0.5 meters. And another important boundary condition or the consideration to be made is in the U velocity boundary condition. So for the moving body or for the cylinder which is moving, so you need to assign the moving velocity in this case. So these are the important or the highlighted changes that needs to be made for dynamic mesh or for the moving boundaries. Okay, now let's see the results. So you have option to choose between reconstructed case and decomposed case. So in my case is still decomposed case. I have not reconstructed it yet. So decomposed case means that it is distributed in different processors. So I have not reconstructed into a single state. So if you run this case, then you can see how the deformation of the cells are taking place, meshes are taking place according to the movement of the boundary. So as we go farther, the inverse distance, as we have used inverse distance, that is, as we go farther away from the boundary in these regions, the cell deformation will be very less compared to the cells near the boundary. So you can, so after this, let's see here the velocity profile, velocity contours. So I have ran for the end time of 2 seconds because that is our time period. So I've ran for the one single cycle from mean position. So if you want to compute vorticity, then you can also do that. For that, you need to go to filters, alphabetical, and there is a filter called gradient of structure data set. So you can see that there is a gradient of unstructured data set is present as filter. So if you go there and choose velocity and then compute vorticity, and then you can choose vorticity from here. So you can see that the vortex shading is taking place in the cylinder, and the carbon and the vortex state is being formed behind the cylinder. So the vortex state will depend on the reduced frequency and the amplitude of the cylinder, moving cylinder, oscillating cylinder. So that it might be the standard or the carbon vortex state, or it can be reverse carbon vortex state depending upon the reduced frequency and amplitude. So yeah, that's it for this case. So in this way, we can simulate the dynamic meshing, or we can simulate the dynamic movement of the boundaries also using the dynamic meshing strategies available in OpenFOAM. So yeah, you can do other post processing as well, like computing the drag and computing the drag coefficient, lift coefficient from ParaView also. So that is also done in previous workshops. So in the previous demonstrations, so you can check out those videos of the previous FOSSEE workshops also. So I think thank you all. Uh, Thank you all. I think you got to learn something from these short demonstrations.